Hoover High School AP Chemistry. This is your assignment, day 69, the week before the Christmas winter break. It was assigned on Monday. It was originally designed to be due on Friday, but I've been slow getting up some of the videos and getting the answers to you, so definitely come back on January the 3rd. It's actually January the 4th. Come back Monday, January the 4th, and have this done because you're going to need this for the week right after the break. It's very, very important that you understand these concepts. All right, I'm going to go ahead. I'm going to leave the first page and a half to you. Those are question answers that come out of the video. And I want you to watch the video. Watch it very carefully, even a second time. There's a couple of videos, the basic acid-base and the weak acid-base video. So be sure you watch both of those and are up on that. Okay, so I'm going to leave these questions here. Those questions, so those are for you to answer. And they're all answered very directly in the video. Just watch the video and be sure you understand these concepts here on the first two pages. I will do a couple of these down here for the conjugates. Be sure you understand the concept of a conjugate base or conjugate acid. So conjugate base, conjugate acid are simply an acid-base pair. They're related to each other. They simply differ by a single proton. In other words, by one of these H's. So for example, this one would be, you don't have to write the whole reaction. I'm just going to do it for this one. Okay, so it's formic acid. It's going to lose one of the hydrogens, gives up one of those, and it becomes a formate ion right there. It gives that proton to water, and there you have hydronium in the water. That's what makes it an acid. That's the definition of acid. It creates hydronium ions in the solution. Does it matter which H you take, this one or this one? Usually it's the one on the end, this one. And now this is hydroiodic acid. That's a strong acid. So if there's one on the end, that's usually the one you take. So the answer to this is this. So this is the parent acid, and this is the conjugate base. These are weak acid, weak base. Okay, you can do the other two. You're going to see plenty of examples with acetic acid if you haven't already, and HI. That's hydroiodic acid. Okay. Down here, I'll do a couple of these. NH3, you'll actually see in the video of the solution of one of the problems. We'll go ahead and take this one, and it's just going to be. So this is a base. So it's a negative ion that's going to attract a proton. Okay, so this attracts a proton from the water, and therefore it has two H's when it does that. There it is. And the proton offsets this negative charge, so now it's electrically neutral. This is the conjugate acid. So this is a weak base. This is the conjugate acid. These two are different. Go ahead and circle those. Those are the conjugate base acid pair. And then that produces, what a base does is it produces hydroxide ions by breaking that water molecule and pulling one of those hydrogens away from it to leave a hydroxide in the solution. Okay, I'll leave the others for you to do. If you have any questions, you can ask me on those. Okay, so let me just be sure you have the answers on these. This one you're going to see in the video. This one, it's an acid. It's going to lose the hydrogen. So you're going to end up with an H3O plus, and you're going to end up with an iodide ion. Okay, there you go. I didn't write the water on this side, but so this is the acid, and this is the conjugate base. Now, the conjugate base of a strong acid, base means it will accept a hydronium ion back. It'll accept a hydronium ion. It can receive a hydronium ion. This will never do it. The conjugate base of a strong acid will never take back an H+. If it dissociates 100% of the H+, it doesn't make any logical sense that it would take one back. Why would it take it back? Just so it can dissociate it again? That doesn't make any sense. So it'll never take one back. In other words, this never really acts as a base. You'll never see an H+ come and join that. That will never happen. Okay? So that's true of strong acids. All right, let me do NH3. Okay, add water. I didn't add the water on that, so I should put the water there. NH3, H2O. So one of these is going to jump over there. It's going to become NH4. NH4. And since it was just a proton without its electron, it has a positive charge now. And like any base, it leaves a hydroxide in the solution. So this is the base, and this is the conjugate acid of that base. Okay, they work in pairs, and I'm off screen, sorry, there you go. Not too off screen. Okay, again, these relationships become very important when we get to buffers after we get back from the break. So finally, one more. You're going to see this one in the video, in the problems, the later problems in this lesson, so I'll leave that one. Okay, let's go ahead and move on now. All right, strong acid reaction. So the only purpose of this is to illustrate why you do not need to have a rice table for a strong acid, because it totally dissociates, okay? Strong acids 100% dissociate. So if we write the reaction for HCl, you put it in water, and what you end up with is hydronium. The H jumps over to the water, and the Cl is left as a spectator ion. It's not going to recombine. In other words, you're never going to have an H come back and jump onto that again, because it's the conjugate base of a strong acid, so it will never take back hydronium. Again, as I just said, why would it do that? Why would it take an H? So it can just dissociate it again? Because it's going to dissociate anytime it's with an H, so it will never take one back. All right, so you start off with 0.4 molar. And you can draw the X's and all, but you don't need to do it here. The water you never take into account. So it's going to dissociate. So all the change is going to be total, 0.4. You're going to lose all of that and end up with 0 at the end, okay? So you don't even need to use X's for this. When this breaks up, in 0.4 molar of this breaks up, it's going to break up into 0.4. You start with 0 here. It's going to break up into 0.4 molar of this and 0.4 molar of the chloride ion. So you end up with 0.4 molar in the equilibrium. And I made a mistake. See if you picked up my mistake. It's a one-way reaction. It never goes backwards. So this should not be a double arrow. This should be a single arrow in that direction. So you start off on the left side with all reactants. You end up on the right side with all products. All reactants, no products. You start with no products, you end up with all products, okay? Everything changes. It's a one-way reaction. As I said, this is never going to take back an H to become HCl. So that's why you never need a rice table. When you see it's a strong acid and they say they put 0.4 molar in the solution, then automatically you just can jump right over to here, because this is what you're interested in. How's that going to affect the hydronium concentration? And there it is right there. It's the exact same number of moles of hydronium as you had moles of the strong acid. Okay? The same would be true of a strong base and hydroxide. Okay, now when we get to weak acid bases, which can go in both directions and which don't go totally from left to right, they go part of the way and then they stop, then we need a rice table to figure out equilibriums. That's when we get into an equilibrium situation. Okay, so we're going to start off with one that we just saw on the previous page. Write a rice table for weak acid, 0.6 molar formic acid. The Ka value for formic acid is 1.8 times 10 to the negative 4th. Okay, so if you're drawing this on paper, just write RICE and write the equation. You don't have to draw the boxes. That's not necessary, but be sure you line things up properly when you do it, okay? So we're going to start off. We don't need the Ka quite yet. We're going to get to that when we get to the law of mass action. So we're going to just fill out the rice table. So it looks like this. We wrote this on the previous page. And if you want to write the plus sign, you can do that. Now this is a two-way reaction, so you can draw a double arrow. Okay, so this hydrogen jumped onto the water molecule to become a hydronium ion. That's what an acid does. It creates hydronium ions. And then you have the formate ion left over. And now it is a weak, it's the conjugate base of a weak acid. It's a weak conjugate base. It's a weak base. It's the conjugate base of a weak acid. This reaction can go back and forth. So this can take back a hydrogen ion, or a hydronium ion, okay? But anyway, let's go ahead and write this. So we know we have an initial concentration, and all you need is an initial concentration in Ka, and you can figure out all the equilibrium concentrations of everything. You can figure out pH, pOH, everything, just with those two pieces of information. So there's our initial concentration here. Okay, you never use water. Now, the truth is you really do know more than one initial concentration, because if they don't give you anything, you know these are zero. You have to have that. So those are zero. You assume there's none of that in solution. You simply threw this into the water, and now it's going to start to react. Okay, so this is going to be minus, because this is going to be decreasing. It's going to decrease on this side, increase on this side, so it's minus x. X is the unknown. That's what we're trying to figure out, is how much is it decreasing, or what do we end up with at equilibrium. And you always use the coefficient, so I'm just going to do it this one time. I'm going to write coefficient there, and a coefficient there, and there. Okay, and I'll write it here, but normally you just write the x. You don't have to write that. But just to emphasize that this and this coefficient, not the negative sign, but this coefficient and this are the same. And it's going to be the same over here. You're adding, so it's going to be plus x, and we'll put a 1 here. This and this are the same. Whatever you had up there, mostly for acids and base reactions, it's always 1s. That makes it a little easier, but it's not always 1s. It doesn't have to be. Well, anyway, when we get to examples where it's not, you'll see it. Okay, over here you're also going to be adding x, and it's 1, that, and that. Okay, so now you go ahead and you add them, or subtract. In this case, we're subtracting 0.6 minus. I'm going to drop the 1 minus x, 0 plus x, and 0 plus x. All right, so these are the equilibrium values expressed as algebraic expression. So we're going to use that to figure out the concentrations of each of these. We're really interested in this one usually, the hydronium ion, but we're going to figure them all out. So, and that's what it's asking, but we're going to do them all. Okay, so now what we do is we need the law of mass action. So that's the acid dissociation constant equals the products on top Now I'm going to do this only in this first problem just to remind you that you do use the coefficient as an exponent. So since it's 1, you normally wouldn't write it, but I am going to write it this time only just to emphasize. Don't forget that you have to do that. You start doing these problems and you do so many of them and you never have to put an exponent there, and so when you get to one where you do, you might forget to do it. Okay, so here's this. And again, it's raised to the first power. And then it's all going to be over the reactants over here. Water is never counted, so it's going to be this down here. Or well, actually, let's go ahead and write it in like this. Also raised to the first power. Okay, so that's the law of mass action, or you can just call it the equilibrium equation. All right, I'm going to go down below then, and I'm now going to substitute in these values, these algebraic values. So the 2 on top are the products. It's these two, so it's just x times x right there. All right, and we have a Ka value now, so we're going to go ahead and substitute that in 1.8 times 10 to the negative 4. Let's go ahead and do that. And on the bottom is this. That's going to be this right here, 0.6 minus x. Okay, and there's the equation. And now we're just dealing with algebra. I'm going to do this one time. I'm going to show you what happens if we don't get rid of that x. Use the simplifying assumption. Okay, so what I will do is I'm going to multiply both sides by this. And these cancel. And what I end up with over here is it's going to be 1.08 this times this, and then times 10 to the minus 4, and then negative x times that. And then that's going to equal on this side x times x, or x squared. So now I have a term with an x squared with an x right there. That's an x. That's a times sign. And then a term that's a constant. So if I subtract all of this from both sides, and I'm going to go ahead and put it all, I'm going to flip it around the equal sign. So I'm going to put the x squared over here. So I'm going to end up with x squared plus this and then I subtract this from both sides, so it's minus that. And that equals 0. So now we have a quadratic equation here. X squared plus x plus constant excuse me, x squared plus the x term, there's the x term there, plus minus the constant here, equals 0. That would require the quadratic formula. I actually wrote that incorrectly. Let me put the x where it should have been. Put a parenthesis there. So that's going to be that whole thing times x. That's your x term. And then the minus sign is right there. So this would be your coefficient there would be 1, so that would be the a, that would be the b, and that would be the c if you were going to plug it into the quadratic formula. So that's messy, and I told you you'll never have to do that, but I just want to be sure you understand the concept. If we assume, however, that this x is really, really small compared to 0.6, what gives us a clue that it is? Well, the Ka value is 10 to the minus 4. That's 1/10,000th. And this is 1/10. This is measured in tenths. This is 6/10, and this is 1.8 10,000ths. So that's really small compared to this. So I'm going to tell you that you can always assume that this is really small and just go ahead and eliminate it. I'll show you that in a second. But you have to show the 5% rule at the end. I didn't do that in the instruction video, but I'll do it here. Okay, so basically what I'm saying is this. I'm going to take all this and kind of skip it, and let's go ahead and rewrite the equation before I did all of this. In other words, you really don't have to do any of that ever. Okay, you're going to do this. There's the K A. Okay, so that's where we're going back to this point, and we're not going to do a quadratic. What we can do is we assume this is really small, so we can just rub it out. It's gone. Okay, now we're not going to end up with a quadratic situation like that right there. Okay, that's just wanted to make that point one time, and you won't have to deal with that again. Okay, so now we're ready to go ahead and do the algebra on this. So it's going to be, you're going to multiply both sides by 0.6. And what you'll end up with is x times x, these will cancel. X times x is x squared. I'm going to put that over on the left since that's where we usually put the variable. So x squared equals this times this. So again, that's 1.08. Okay, now you take the square root of this side, and you take the square root of this side. And the square root of x squared is x. And the square root of this over here is something you knock down on the calculator. Be careful doing square roots of scientific notation. I'm going to come over to my calculator. I'm going to do second and x squared. Let's focus here. Second and x squared, which is going to give me a square root function. There you see it right there. And it's 1.8 times 10 caret negative 4 and close the parenthesis. And you get 1.34 times 10 to the negative 2, or you can just write it like this. It should have been 0.0134. And that's a few extra significant figures there. Do that. So that's your value of x. Okay? So what does this value of x mean? Well, we come back to our Rice table up here, and we see where we find x. There's x. What is that? That's the equilibrium concentration of the hydronium ion. That's one of the questions that it's asking for. So let's go ahead and write that. Again, this means at equilibrium when I write this. That's equilibrium. The brackets mean concentration. And you should put molar behind it. It's moles per liter molar. Okay, it's a concentration. All right, I'm going to go ahead and answer the other two. It's the same for the formate ion right here. Okay, and let's go ahead and figure it out for the equilibrium concentration of formic acid. So it's a 0.6. Let me write that way over here. I'm going to need a little space to work. So we'll do this on the calculator right here. 0.6 minus 0.0134. And that gives us 0.58. You see it didn't go down very much. 0.58, 0.59 we'll call it. Okay, so it went from 0.6 to a little less than 0.59. That's only 1/100th. Not very much at all. So, and that's what we said. We said we're assuming that x, which is this number right here, is very small. This number right here is very small compared to this, so you're not going to see much of a change there. Okay, let's go ahead and figure out the pH of the solution, and while we're at it, we'll figure out the pOH and the hydroxide ion concentration. Okay, so let's go ahead and figure out, we know the hydronium ion concentration, so the pH equals negative log of the H3O. Again, this is straight off your acid-base roadmap. And here it is right here. Try to find a way to get this printed out, or I would say it's important enough I would copy it. Just make a neat copy of it by hand. If you don't have any way to print or copy anything, make a neat copy of that by hand. And you keep that in front of you whenever you're doing these problems. You're going to need it definitely to finish this week and for next week as well. Okay, so there we go, is that. So that's going to be the hydronium ion concentration right there. And it gives us 1.87. That's a pretty low pH. That's approaching strong acid, even though formic acid is not a strong acid. That's a pretty low pH. Now remember, pH, and this is something I talked about on the instruction video and wanted you to answer a question on the first page. pH is a function of two things: how strong the acid is. Formic acid is not a strong acid, it's a weak acid, but also how much you used. Okay, you use enough, you can get a lot of hydronium ions in the solution, and that'll make up for a low pH as well by just having a lot of a weak acid. Okay? All right, let's get to POH. And the formula is simply POH plus pH equals 14. That's assuming 25 degrees, and unless stated otherwise, you can go ahead and assume that. It's just one of those assumptions you can make. All right? So that means that this and that's going to become 12.13. So this is that. Okay, that's the POH. Now the hydronium ion concentration. So this is one problem. This is a second. Now we're going to do a third. The OH. There's two ways you can compute it. You can say that OH times POH equals 10 to the negative 14th, or probably a little bit easier way to do this. It doesn't matter. You're going to say it's equal. You get this again off the acid-base roadmap. It's 10 raised to the negative POH. For OH, you raise it to the negative POH. For pH, you'd raise it to the negative hydronium. So I'm going to do this to the negative OH. That's this. And it's going to be very small because you put an acid in the solution. That's going to make it more acidic and less basic. The two work together, more of one, less of the other. Okay, so it's 10 caret, raise it, negative 12.13, and we get a really small number. It's 7.4 times 10 to the negative 13. Really small number. Okay, I mean you're in the trillions there. Okay. All right, so that's the OH, and that's that right there. Okay. Now, one more thing we have to do that I said we had to do in the video, and I didn't do it there, is the 5% rule. So the 5% rule states that the relationship between the value that you got for X, which is that's the hydronium concentration, that is less than 5% of the original concentration of your acid, which is 0.6. And then you multiply that by 100, and that'll give you the percent. It's got to be less than 5%. So I'm going to just draw another little line here. So it's going to be 0.0134 over 0.6. That's the X value. That's the original concentration. And then you're going to multiply that by 100 and slap a percent sign on the end. So that's going to give you this. And it gives you 2.2%. And that's below 5%. So that means it was valid for us to just take that X, or down here we did it, and just scratch it out, just get rid of it, and only use the 0.6 because it's such a small value compared to 0.6 that it was a valid assumption. Okay, and they came up with if it's less than 5%, you can do that. If it wasn't less than 5%, that's all I will want you to write. I don't want you to go back and redo the problem with the quadratic formula. That's what you should do, but all I want you to do is explain. Okay, so you can, I'll just give a quick explanation, okay? You can use other wording. The elimination of the value of the X was justified. Okay, and that's it. Okay, that's really what you're saying by that. Okay, let's keep going on these. And I'm going to try to limit these to 30 minutes. And I'm at 30 minutes. So you can get them in bite-sized pieces here. And I'm going to go ahead and wrap this one and put the next one on another video.